So welcome back, guys. This is day 12 of rotational dynamics, and we are at the idea of angular momentum. And one of the students asked me a question regarding a helicopter. I mean, he didn't really ask the entire question, but I got an idea. I mean, I should ask this in every class. In a helicopter, let's say there is a body. I'm not entirely drawing a helicopter. Don't expect me to draw. And the propellers, the wings, or whatever you call it as a propeller, and there is a tail, and there is a smaller propeller at that end. Okay, so let's just imagine this looks like a helicopter. Okay, so the question is, what's the purpose of this rare propeller? Can we just switch it off, or can we just take it off and yet expect the helicopter to go in a equilibrium or go forward? Definitely not. You might have seen this in a lot of movies. Whenever this rear propeller fails, even though this is running, even though the main propeller is running, when the rear tail propeller fails, the helicopter immediately crashes. Not just directly crashing, you can see it actually going around and around and around, and then it crashes, right? So one of the, like, you might have overseen this concept, but clearly observe one thing: the body is creating some torque and creating an angular velocity for the propeller. If the body is putting some torque on the propeller is putting some torque on the body in return, right? An important point is, if only the body is standing on the ground, if only the body is standing on the ground, there is no problem, because the ground will give you the stability. But that is not the case. Helicopters are not supposed to, they're not designed to stand on the ground. They're designed to fly in the air, right? What happens is, like, whenever you create this torque, the propeller will create some opposite torque on the body. So in reality, if you switch on the propeller of a helicopter, it actually rotates the body in the opposite direction. If the propeller is going clockwise, it rotates uh, the whole body of the helicopter in the opposite direction. To stop this, to stop this, we have a smaller propeller here with a long tail length, because if only we can create some small force here, if only we can create some small force here with the perpendicular length, it is creating some torque in the opposite direction. It is creating some torque in the opposite direction and making the helicopters go stable. That is the main purpose of the rear propeller. Now Aditya is asking to counter the torque by propeller to prevent the helicopter by rotating. Yes. So this rear propeller has a clear purpose of balancing the helicopter. Plays a really important role in the balancing the helicopter. So it's not just some random thing that you can simply have it for turnings. Like some students said, you can simply use it for the turnings. It's not just for the turnings. If you switch it off, the helicopter will go around and it will also crash. Some Karthik is asking, how will it go forward? So the basic thing is, like, there are a lot of operations. First of all, this can tilt. Okay, the whole body can in fact tilt. So whenever you're tilting, it's not just you're giving some upward thrust, you're also giving some forward thrust. How do they make the body tilt? If you rotate this with some enough angular velocity, the body will create a vertical angular momentum also. So it actually creates a tilt like that, and you can control the whole helicopter in different directions. Okay. Aniket, what is it?
Sir, but I didn't understand why will it crash? It can just keep rotating and moving, right, sir?
Yeah. It can just keep rotating and moving. Yeah, that is a possibility. But can you ride a helicopter while it's just rotating constantly? It won't crash for
Okay.
sure. It won't crash for sure. But people lose control of it if that is happening. Like how do you expect a pilot to actually control a helicopter which is actually just rotating? It's not. If pilot is God, yeah, then maybe. And yeah, so that is the idea about the helicopters, guys. So the conservation of angular momentum is actually working here. The idea of conservation of angular momentum is actually working here. So this is an important point I just wanted to convey. Now, talking about angular momentum, I need to ask you this question also. If you people have an answer for this thing, which is called as the gyroscopic effect. You've all seen this toy working. Okay, yeah. How is this working? How is this balancing itself? Does anyone have any answers to this question? If you do, please raise your hand and speak about it. If you want me to explain this, I'm actually making a video on this, so which will be ready by tomorrow. I mean, it is ready right now, but there are a few last minute changes that I need to do. So once it is ready, you'll get to see how it works. Chetan, tell me I mean, what's your answer about it?
Sir, the torque of this gyroscope will rotate it.
No, so that's it. That's the answer. Like I need a better explanation to that.
Okay, sir.
Yeah, so you can clearly see one thing, that the angular momentum of the body is going around like this, right? The angular momentum of the body. When you have a body which is rotating like that, you clearly have an angular momentum which is in this direction. It is constantly rotating. So that's what makes it, I mean, I'll have a clear explanation later. People are still coming to the class. Yeah.
Sir,
Tell
the
me.
angular momentum of that body is going to balance it from falling off, right, sir?
Yeah, you can simply say that, but wait for the explanation that I'm going to give tomorrow, which makes more sense to you. Aditya, what is it?
So with this, I wanted to say the same point only. Is this applicable with while we write cycles?
Yeah, exactly. But when you're riding a cycle, it's a lot more complicated. It's not this simple. This is very simple to explain. I mean, this is also complicated, but compared to this, explaining a bicycle is a lot more complicated thing. Okay, like whenever you see a wheel rotating, it has some angular momentum, and whenever we say angular momentum, what is momentum? Momentum is having some inertia, right? Like a body going straight in the straight path, it has a linear momentum. It won't immediately change its direction. You have to put some effort to change its direction. It's a similar thing. Okay, so
Yes,
you'll
sir.
get to see how it works tomorrow. Like tomorrow I'll post the video most of all. Okay, how long can a gyroscope spin? Vivek asks. If there is no friction, it will spin forever, but you see that joint it is standing on, there is friction there. There's always friction there, so because of that friction it will slow down eventually and will fall off. Okay, so gyroscopes cannot just go forever. They will definitely fall at some point. Okay, so you'll get to see the explanation of this thing tomorrow. Let us move on to the bigger ideas. I hope you've done enough problems on angular momentum, but let's just discuss one or two more problems on it and move on to the idea of angular impulse. And today I'm going to introduce the idea of kinetic energy also. I mean, we've already introduced, but we are going to solve some problems on it. So let us, we've already looked at this problem, right? Where a disk is already at rest and a man or a particle come running and standing, I mean, like jumping onto the wheel, and they're combinedly rotating. We've done this kind of a problem. All you need to do is the initial momentum is basically mvr, the final momentum is moment of inertia of the disk plus moment of inertia of man into omega. You simply equate these two, you'll get the answer. We've done this kind of a problem. I'm going to show you a similar kind of a problem where a disk, this is the top view, disk is hinged at the center. It is connected to a thread via a ball, of mass m. Let's just say the mass of this thing is 5m. Okay. So, and this mass is given a velocity v. What is a case, what is a situation right after the string gets taut? Do you remember these kind of problems in collisions? We used to do the same kind of a problem in collision, but there is a thing that I used to tell you, like whenever you see a problem with string, what you need to do, when you see a spring, what you need to do. Does anyone remember what you need to do in this kind of situation? Anybody? No? Yeah, Niket?
Sir, apply constraint relation.
Constraint relation, you don't really need constraint relation, but do you remember these kind of problems where one body is like this, other body is like this? Once the string gets taut, it remains taut and they go with a common velocity. Do you remember these problems?
Yes, sir.
So what did we do? We used to consider this thing as a inelastic collision, if you remember that. We used to consider this thing is similar to an inelastic collision. If only we have a spring in between them, we used to consider this as an elastic collision. Like, do you remember that bit at least, Aniket?
Yes, sir.
Yeah. So we are exactly doing the same thing. We are simply expecting this to behave as an elastic collision. So once a string gets taut, this body this point on the disk, they move with a common velocity, v common. Or you can simply convert this problem into this problem where a disk is hinged here, a particle is coming with a velocity v and sticking to the disk. You remember those kind of problems? It is a similar problem. Like you can completely happily do this problem in this perspective. You can happily do this problem and solve this problem in that perspective. Nothing's going to change the answer. Okay, it is exactly the same thing. You will get the same answer as if let me take a page. Let me show it to you anyway. Like when it is like this, when it has a velocity, initial angular momentum is mvr, but when the string gets taut it has some v1. Let's just say this has some omega, and you write the angular momentum of this thing as mv1r. This for the disk it is I omega. So you equate this value and this value, and also you have one more idea saying v1 must be equal to the velocity of this thing. This must be also v1. So v1 equals to r omega. You use this idea in this thing, equate this value to this value. What you did is basically conserving the angular momentum. So if you do this, and you will definitely get the value of v1 or omega or whatever the value that you want to get. Okay, now once you're clear about that point, what's the next thing that I should be discussing? We can move on to the idea of angular impulse already. Did I discuss any angular impulse problems? Aditya and Aniket both have raised hands. What is it?
Sir, in the previous one, it will eventually stick to it, right, sir?
No. After this thing, a lot of troubling motion happens because this thing is trying to go like this and this thing is trying to rotate. It's not really the thing that we are expecting. But at this instant, this is what happens. At the very instant, this is what happens. After that, the problem takes a very different turn. So we can't really expect it to go in a specific path. Okay.
So we'll study that, sir.
No, we don't. It gets complicated. It gets very complicated.
Okay.
Yeah, tell me, guys. Next.
So here you have put that string in the tangential position to the disk, na sir?
Yes. That's a good question.
Instead of that, I put it here in the middle, this
That's
middle part, sir. Like
that's a good question. Like I can connect it here. The disk is
yeah, or
here.
just in the line of hinge only.
If it is just in the line of hinge, there is no problem at all, because like let us say this is the velocity. What is the initial angular momentum?
Then it will be for the same only, na? We can
No,
consider it as linear.
there is no perpendicular distance at all. So initial angular momentum is 0. So once the string gets taut, it simply stretches and it simply stops like that. That's all. It won't even move.
Yes, sir.
You get that? Because here also the angular momentum 0, here is also the angular momentum 0. Otherwise, if you connect it at somewhere here,
Some random position, sir.
in some random position, you need to write this perpendicular distance. That's all. That perpendicular distance and write the angular momentum and all. Okay.
Okay.
Yeah. After this, we are coming to the point that I told you that I would discuss later. How do you write the angular momentum of a body which has both linear velocity and angular velocity? Let us say there is a body whose center of mass has some velocity v center of mass, and body also has a omega, and I want the angular momentum of this whole system by some random point, some o. I want the angular momentum of this body about this point, about o. How am I going to do that? Now I can tell you the enlarged method, which is where I take some random point. I take some random point. So for this random point, there is already VCM and there is R omega. I mean, like if you take this as R, so there is R omega. All I need to write is the angular momentum of these two velocities with this perpendicular distance. That is what I need to do. Once I do that, I'll get the answer. Okay. But if I do this whole method and write the sigma and all, I will get a very simplified version. I'm directly jumping to the simplified version. I'm telling you, like you can do the method. You can write VCM separately. You can write VCM is because of the linear velocity. R omega is because of the angular velocity. Anyway, in any case, the point all has a common as a velocity of the resultant of VCM and R omega. So this resultant velocity about this point, if I write the perpendicular distance, let us call it as D. Using that all and using a sigma for all the points, you will definitely get the answer. But I'm directly taking you to the answer itself. Whenever you see a body with a linear velocity and with some angular velocity, and you want the angular momentum about a random point O, what you need to do is take the VCM and perpendicular distance. First of all, consider this as a point mass and write the angular momentum. Consider this whole thing as a point mass. So m into VCM into D, m into V into perpendicular distance. That is the angular momentum of the center of mass, plus I omega. I about center of mass only. I about center of mass into omega. That is the angular momentum of this body about O. This is L bar about O. L bar about O. I hope you are clear about it. Whenever you see a body, that is how you write the angular momentum. I'm going to give you one or two problems. Sir, if the velocities are not constant, then also will it work? Yeah, at that instant, that is a value. The velocity is not constant. Yeah, the velocity will change after some time, but the angular momentum at that instant should be this. At the next instant, it will be a different value, but even at that instant also, you do the same thing. You take the center of mass. I'm going to give you a question and you will clearly understand, okay? Take a square plate. Take a square plate whose center is going with V. This is going with omega on XY axis, and this distance is 5 units. Mass is m. I want the angular momentum of this body about origin. I want the angular momentum of this body about origin. How are you going to write? Can somebody like raise your hand and tell me the answer? Anybody is appreciated. No? Guys, it's easy only, right? First of all, all I need to do is L about center of mass, sorry, L about the origin O is, first of all, m into V into 5 units. Simply considering that as a point mass. So m into center of mass velocity, V into perpendicular distance is 5. So m into V into 5 plus what is the moment of inertia of a square plate? It is ma square by 6 as far as I remember. So yeah, that needs to be given, ma square by 6 into omega. This is the angular momentum of the body. Okay. Now I'm going to twist this thing by a little value, by a small idea. The same thing is going like this. The same perpendicular distance 5 units. The same square plate, except it is rotating like this. Can somebody tell me what will be the angular momentum? Is there any difference? Here the angular velocity is like this. Here the angular velocity is like this. Chetan, you can speak.
So just take it minus, sir.
Exactly.
Take that angular moment, this angular velocity minus.
Yes, guys, very simple, because you can clearly see one thing, because of the VCM about this point VCM, the angular momentum is clockwise. This is also clockwise. So that is why I write both of them as positive. Here, about this point, I want the angular momentum. You can clearly see for VCM, it is clockwise only, but this is anti-clockwise. So when I write the angular momentum L about O, I write m into V into 5 units minus I omega. I is ma square by 6. You can fill the value. Minus I omega. So whenever you see a body which is having a linear momentum and an angular momentum, this is how you write the angular momentum of the body. Okay. So let us switch into our important
Excuse
question
me,
here.
sir.
Yeah, tell me.
Sir, is it necessary that should I take that angular velocity only in negative?
No, it's
If
not
I
really
take that
necessary.
positive and
You
this
can,
velocity
you
negative.
can definitely take that, because, but once you define a specific direction, stick to the direction.
Yeah.
Okay.
Okay.
Once you say clockwise is positive, stick to clockwise as positive. Or if you want to write anti-clockwise as positive, just stick to that and don't change it. Okay.
Yes, sir.
And I'm going, yeah. So once you're clear about it, I want an answer for this question, guys. What's this value? A rod whose center is going with V omega, V omega. I want the angular momentum about center. Perpendicular distance is 10 units. Can somebody give me the value? It's a rod that has a linear velocity, angular velocity, and also I want the angular momentum about the origin. Chetan, yeah, tell me.
Sir, 10 MV minus I omega.
mv into
10
10,
minus
because I have to give mass and length also. mv into 10 and
minus I omega.
I is nothing but ml square by 12 into omega.
Omega.
You see that? So this is how you write the angular momentum of a body. This idea is so important in a lot of problems. You will get to see those ideas tomorrow, like why writing angular momentum is so important. Aditya, what is it?
Sir, here we should not relate this omega and velocities, na? We cannot relate it, na, here.
How? What do you mean relate? Like velocity and
Like
omega?
I cannot write here, na, like r omega is equal to v.
No, I cannot write. Like there is no relation. There is no constant relation here. Like if only something is connected to something, if only something is connected to
Yes,
something
sir.
else, then yeah, definitely I can write it. Otherwise, I don't have the right to do it. Definitely no.
I wanted to
Okay.
clarify.
Yeah. So after that, shall we look at this problem or I want to talk about angular impulse first of all. I've already talked about it. Angular impulse. Did I not talk about it? I talked about it, right, Aniket?
Yes, sir. Sir, I had doubt in previous one.
Yeah, tell me.
Sir, that I omega should be taken along which point?
I omega is about center of mass only. Like I mentioned, this is for the body about O. So this is about O only, this value. Now this value is about center of mass.
So, sir, the axis should be taken like vertically or horizontally?
Since you're talking about rod rotating like this, about this axis, so it is like you're talking about axis of rotation of the body, right?
Yes, sir.
So an axis that is passing through this point perpendicular to the page. That is how the axis is.
Okay, sir. So, for 3D bodies?
But 3D bodies also, it depends. Like you will get to see a lot of situations, like maybe a cylinder or a disc. The axis is this only. Like they have to mention about which axis it is rotating. When I said omega, I clearly need to mention that this is rotating about specific axis. Okay.
Okay, sir.
Yeah.
So, we can't take along origin.
What? The moment of inertia?
Yes, sir.
No. This is how you get it. Like you can take it, but that involves a different method. So let's not do this. Like completely stick to this method only. Okay.
Okay, sir.
MVD into this value, like MVD plus the angular momentum about its center of mass. Let's just stick to this value, and you'll get an easier ideas. I mean, you will find it definitely easy to find it. I mean, solve the values in this style. Okay.
Okay, sir.
I was gonna discuss something. Yeah, the angular impulse. So like I mentioned, angular impulse idea is also like, let us say you have a rod which is hinged here. It is hinged here. And let me just give you a problem. Why don't you give me the answer? I've given an impulse J at a distance L by 4. So once I give the impulse, the rod starts to rotate. Neglect gravity and all. What is the angular velocity? Can somebody tell me what is the angular velocity? If I give an impulse J, what will be the angular velocity? Guys, somebody needs to speak. I mean, like, are you trying to solve the problem? Then go ahead, it's fine. What is the angular velocity when I give an impulse j at a distance L by 4? I've already talked about it. Angular, this is the linear impulse that we gave. This is into perpendicular distance gives you the angular impulse. So let's try it along. Okay, somebody already gave me the answer saying okay 3j by ml. Let's just check. So the angular impulse j into L by 4, the angular impulse here that you give as j into L by 4 equals to I into omega. Angular impulse that you give is j into L by 4 is equals to I into omega. Now j into L by 4 equals to I is about which point is it rotating the rod? About its center itself. So ml square by 12 into omega. L cancels 4, 3. Omega equals to 3j by ml. Who gave the answer? Sai Harshita Challa. Yeah, you gave a good answer. So the answer is 3j by ml. So guys, this is how you solve the problems. I'm going to give you one more question. A squarish plate, mass m, side A, hinged at its center. Somebody gave an impulse j here. Try to find the answer right after the impulse. At what angular velocity the square plate is going to rotate? At what angular velocity is it going to rotate? Let's try it and give me an answer quick. Any answers, guys? Anybody? Mazida already gave an answer. Good. Okay, everybody's giving the same answer except Naga Pragna gave a double value. I think she got something wrong. It's quite easy only, right? Because you have a perpendicular distance A. So the angular impulse that you gave is J into A. The angular impulse that you give is J into A, which is equals to I into omega. I is nothing but MA square by 6 into omega. Sorry, omega. A cancels out. Omega equals to 6J by MA. Okay, 6J by MA is the answer. Why did everyone give 3J by MA? Oh, this is A by 2, right? I'm sorry. I'm wrong. So the answer is 3J by MA. That's good. Okay. So that is the answer, guys. This is how you simply solve this problem. Now, what if the body is not hinged? What if the body is not hinged at all? Like the same rod only, it's not hinged. Now you give some impulse. We've done this kind of a problem. We used to give force without a body which is for a body which is not hinged. We used to give a simple force for a body which is not hinged. Now I'm giving an impulse. So whenever this linear impulse is given, obviously the body will get into a motion where after this impulse, the body will simply get into a motion where it has some linear velocity and also angular velocity, right? Since it is not hinged. If only it was hinged, it's simply you can say. Aniket, what is it?
So the impulse is being treated just like the force, right, sir?
Yeah, exactly. Except
All
we used to
formulas
write
are same.
force equals to I alpha. Here we write impulse equal to I omega.
Okay, sir.
Yeah. So what will be the answer? You can simply say, I mean, let me just give the perpendicular distance anyways, and from the center, L by 4. So you can happily write first the linear momentum J equals to mass into velocity of center of mass. That is done. And also J into L by 4 is also can be written I equals to I omega. So you do the same thing VCM and find omega. Shall we do this question? Why not? Why don't we do this question? J equals to MVCM. So that gives VCM equals to J by M. And from this J into L by 4 equals to ml square by 12 into omega, L cancels 4 3s, omega equals to 3j by ml. So for this problem, guys, I have a rod traveling with j by m. I mean, the center of mass traveling with j by m, and it is rotating with a 3j by ml. Rotating with 3j by ml. Somebody can ask you the velocity, the final velocities of some point, some random point, like what is the velocity of this point, or this point, or this point, or this point, or this point. How are we going to do that? This is a good question. Like there's a chance that somebody can give you a question like an impulse is given to a rod which is not hinged. What is the velocity of this point, this end, or this end right after the impulse? Aniket.
Sir, the omega part you can multiply with the distance from center of
Exactly,
mass.
right. That's all. So you can simply consider this as a combination of linear velocity. So because of this linear velocity, the whole body has linear velocity v. So every particle has j by m, j by m, j by m, j by m, and j by m. Because of the rotatory motion, which is rotating like this about center, we can say this part is going with L by 2 omega in this direction, this part is going with L by 2 omega in this direction. If somebody asks you about this point or this point, this goes with L by 4 omega, this goes with L by 4 omega in this direction. So you can multiply with this value. Let us talk about this end. Okay, L by 2 into omega is how much do we get? It's 3j by ml, right? 3j by ml. So LL cancels out. I get 3j by 2m. Guys, clearly observe this bottommost particle has j by m in positive direction and 3j by 2m in negative direction. So the resultant is basically j by 2m in the negative direction. So the velocity of the bottommost particle is this value. I hope everyone get it. Okay. Can somebody tell me the velocity of the topmost point? This has j by m in this direction. Because of this, you have the same value, which is 3j by 2m. So the summation of these two, because both the velocities are in the same direction, 3j by 2m and j by 2m, you will get 5j by 2m in the positive x direction. So these are some basic problems, guys. Like they might ask you these kind of problems. Aniket, what is it?
Sir, suppose that bottommost point is not moving only, like it's zero.
Why would it not move?
Like it sums up to zero, sir, the angular and the linear
Which
velocity.
means it will actually stay at rest. This is an interesting question. Like, okay, so they ask you questions like a rod which is not hinged, and I'm supposed to give an impulse j. By what distance from the center of mass should I give it? By what distance from the center of mass should I give it so that this bottommost point velocity is zero? This is the kind of a question that you can get. Note down this as a homework and try to do it. By what distance, by what x value should you give the impulse such that the bottommost point's velocity is zero? This is a very interesting and good
So
question.
once you can show what this looks like when it actually happens.
It simply rotates like this. I mean, like this is original situation. I mean, the original condition, and the body rotates like this simply. So the center of mass definitely has some velocity, and that r omega is also there. You will get different velocities for all the particles except for this particle, which is at the end. It doesn't really.
So it's like hinged in that place.
Yeah, at that instant, yes, exactly. At that instant, it doesn't really have any velocity. Maybe after that, you will get some forces from this rod and all. It will definitely move after that, but at that instant, it will not have any velocity. The velocity is zero. So they can ask you questions like this: at what distance should you give an impulse so that the bottommost point velocity is zero? Aditya.
So if I think like now only this idea came, like if you just think that point as the hinge point only and solve the problem is simple, like how we used to solve when we think like center of mass is hinge.
Okay, you are getting at a very interesting point here. They ask you questions like, let me give you a question, okay? The same question, so the rod is hinged and you give an impulse. The rod did not move horizontally. It just simply has some angular velocity, which means the hinge actually gave some impulse. The hinge
Yes.
also gave some impulse. The resultant motion of the whole thing caused this motion. So they give you questions like I'll give you a question where this is a long gone, like I'm telling you, this topic is so huge. You can compare this one topic of rotation mechanics with all the 6 topics or 7 topics that we've already done. Okay, this is that big, so don't worry if you don't completely getting it. There are thousands and thousands of questions. Let us say there is a rod which is already hinged here. Let us say there is already a rod hinged here. They ask you a question like, by what distance from the center of mass you should give an impulse? By what distance from the center of mass you should give an impulse? So it's that there is no reaction from the hinge. There is no reaction from the hinge. That is a kind of a question. Like it shouldn't affect the hinge at all. It is exactly the same question, just like this, where the hinge, the extreme endpoint has zero velocity. Here the hinge has no reaction. It's exactly the same question. Good that you asked this question. Aditya, did you understand what I just said?
No, sir. A bit. I got confused too.
Like even if this point, like you can say the same problem saying the rod is not hinged, but I ask you like this end should have zero velocity.
Okay.
Or I
Okay.
can say the rod is hinged, but the hinge does not have any reaction, which means it should not give any impulse. If
Yes,
it is
sir. Now I
not
got it.
moving at all, why would it give any impulse?
Yes. Yes,
So
sir.
these both ideas, these both situations, the question is exactly the same thing. That's what I'm saying. In both the situations, the question is exactly the same thing.
Yes, sir. Now I got it.
Yeah. So they might ask you questions like this. Okay. Now I'm going to give you a small hint. It's not entirely the idea. A small hint. Do you know, for a disk, let's just say for a disk, for a sphere, hollow sphere or a solid sphere, let's just take a solid sphere. If you give an impulse by a perpendicular distance, which is exactly equal to the radius of gyration, the bottommost point's velocities are zero. Okay, now this is not the point entirely where I'm introducing you to radius of gyration. We will actually prove this idea, but since we're discussing this kind of a problem, I'm giving it to you. So if only you choose to hit a sphere or a disk by a distance of the radius of gyration itself, the bottommost points will not have any velocities at all. Aditya, what is it?
Sir, whose radius of gyration? Sir, disk or sphere?
Like for disk you have to give the disk radius of gyration.
Their
So for the
respective.
disk it is r, it has to be r by root 2. For a solid sphere it has to be root or 2 by 5 r. For a hollow sphere it has to be root or 2 by 3 r. So
Yes, sir.
who, like it depends on the body itself. Like if you're taking a body like that, you have to go for the radius of gyration of that body, hit it there, the bottommost point will not have any velocity. It's interesting, right?
Yes, sir.
So for the rod, the distance should be, Aniket is saying something, but Aniket, why don't you find out and tell me the value? Why don't you find out and tell me the value of X? Take it as homework and let me know if for the rod, is it the same value or not? Okay. Aniket, what is it?
Sir, I just solved it and got that value.
You got the value.
Yes, sir.
You got the distance as root over L square by 12, right?
No, sir, L square by 12 just.
No, how do you get length as L square?
Oh, okay. Sorry, sir.
You will definitely get the value as root over L square by 12. Again, the radius of gyration. So that is the importance of radius of gyration. We will come back to this point for sure, but for now, just let it rest. Okay, let's just take it as a point that you know, that you can understand. Let's just remember this point and let it be. Okay. So guys, that is the idea of angular impulse. Also, we can go further and I can trouble you more, but I don't want to do that right now. I want to discuss more questions, but once you practice enough, then only we can discuss all these problems. Okay. For now, I want to talk about the rotational kinetic energy. We've already defined this thing. We've already defined the rotational kinetic energy of any body which is rotating. Can be written as half I omega square. We already do that. Could you show that radius of gyration of a sphere and disk, sir? Sharath is asking, Sharath, are you asking me to prove this? You can do it. You can do it. And Sharath, raise your hand and speak. Sharath. Yeah, Sharath, tell me.
Sir, I just wanted to note down those values, sir.
Oh, fine. Go ahead and do it. I mean, like, it doesn't really matter, like, what kind of impulse, it doesn't really matter. It's about this distance only. You can check and tell me, okay? So, yeah, we are talking about rotational kinetic energy, which is basically half I omega square. It's a very simple thing. And let us say a disk is rotating, a sphere is rotating, a solid sphere is rotating. How do you write the moment? The kinetic energy, the rotational kinetic energy of the whole body, if it is rotating with I, sorry, if it is rotating with omega, you simply write half 2 by 5 mr square into omega square. This is the rotational kinetic energy of the sphere. Okay. Now, once you clearly know about the rotational kinetic energy, we are going to talk about work and power tomorrow. Okay. Work and power can be talked about tomorrow, but I'll just give you a small glimpse of what rotational kinetic energy can basically do. I'll give you a very small problem. Okay. Let's just talk about a very small problem. A rod again. Rod is always the easiest thing to talk, so I take it hinged at the middle. Let me just clean this off. Hinged at the middle. The rod is hinged at the middle, and is this a better way to do it? No, let's not take a rod. It's easier to take. I have another idea to take. We can easily take a disc. Okay, a disk of mass 5m has a particle mass 2m. Somebody moved it, so it started rotating, and after some instant, after at a point, that particle mass came down here. Particle mass came down here to this point. So somebody is asking you at this instant, what is omega? How much is omega at this instant? This is not some instant. This you can definitely not conserve the angular momentum. Let me write that. We are into the topic of rotational kinetic energy, and clearly observe this point that I cannot conserve angular momentum anymore. Can somebody tell me why I'm not conserving the angular momentum anymore? Anybody? Aditya, why?
Sir, because we are providing some external force to move that thing, na sir.
What is the external force?
Some external, then only it will move, na sir.
No, sir. Gravity.
Okay,
When
yeah,
the particle is
gravity.
here, when the particle is here, when the particle is here. We never discussed the idea of gravity until now. We always neglected. I either gave you a problem where there is no gravity, or if we take in a disk, like the gravity is here. So, like in this problem, or in this problem, or in this problem, like any of these problems, the gravity is just acting here. So we never really bothered about gravity. It's just acting on the hinge itself. For the first time, the gravity is acting as an external force, so we cannot conserve the angular momentum anymore. Angular momentum topic is clearly over. So
Okay,
to write this thing, I use another idea saying energy, conservation of energy now. Do you remember how we used to write? Basically, the potential energy here is converted into the kinetic energy here. The disk center of mass did not change its position. The disk center of mass, it stayed there only. But for the particle, it came down by a distance 2r. So it used to have a potential energy. Now it completely lost that potential energy. I'm sorry about that. now it completely lost the potential energy. So I'm going to write the potential energy initial is the mass of that particle 2m g into 2r is the height. I hope you're getting it. For the disk, I'm not writing because the disk center of mass did not change at all. It's just a particle which came down by this distance. So the potential energy is this much equals to, now it got completely converted into kinetic energy. Now, when you write the kinetic energy, it's not just the particle, it's a disk also which is rotating. So I'm going to write half I omega square for the disk plus half 2m into v square for the particle. I hope you're clearly getting it. Or you can directly write half moment of inertia of the disk plus I of particle into omega square also. You can write both the ways. It's totally fine. Let's just write it this way only. Like why depend on that method? You can completely write the entire energy is converted into rotational kinetic energy. So I'm going to write the disk moment of inertia is how much? Half mr square by 2. So 5m is the mass, r square by 2 plus particles moment of inertia 2m into r square, basically mr square. So 2m is the mass into r square equals to omega square. So 2mg into 2r. You have to solve this entire thing. You'll find the value of omega, and that is how you do this kind of problem. This is just a glimpse of the idea of rotational kinetic energy. But tomorrow in the class of next discussion, I will completely give you a lot more ideas about rotational kinetic energy. Once we are clear about rotational kinetic energy, we cleared, I mean, like we covered the more, I mean, like the vast theoretical part of rotational mechanics. From this point onward, we will be only doing the problems. Okay, we will be discussing the problems. We will be discussing little ideas. But the most important theoretical part is clearly covered once we are covering the rotational kinetic energy also. Aniket, tell me.
So that potential energy, I didn't understand.
Yeah, which part did you not understand?
This formula, sir, for potential energy.
MGH. Don't you remember MGH? Mass into g into height. 2r is the height. That's all.
Okay, sir.
Yeah. So basically MGH, mass into g into height. That's all. So that is it, guys. That is it for today. Yeah, I've taught a lot today. This could be one of the most complicated classes that you've gone through until now. I'm suggesting you to watch this video again. Please do that, and because we discussed a lot. But once we discuss more and more problems, you'll get more clarity. So don't worry about it. Aniket, what is it?
Sir, how will it rotate if the particle is exactly at the top?
It's not exactly at the top. It is a little tilted. If it's exactly at the top, no, you cannot say it is rotating. Yeah, that's a good question. If it's exactly on the top point, no, it won't rotate. Let's just say somebody tilted it. I mean, like give a small push so that it rotated. Okay.
Okay, sir.
Yeah.
Sir, after that, how will the equations change? Like,
You will get to see a lot of problems tomorrow. Okay. I mean, like I'm going to ask you, like I'm just giving you one problem for today. Okay. Like you have a rod which is hinged here. So somebody tilted it. So the rod has almost came here horizontal with an angular velocity omega. What happened here? The center of mass lost the height by h by 2. So the potential energy mg into h by 2 is now converted into what? Half I omega square. That is how do you clearly see the equation now? Aniket? Aniket?
yes, sir.
Yeah, so like it's simple, right? Like the disk, the rod started rotating. By this point, it has some angular velocity. How much is that angular velocity? I took potential energy, converted into kinetic energy, and I wrote it. When
So
you
we
write,
can do same, right? If it is still rotating, we can take the sine theta and do.
yeah, if let's say somebody asked you at this angle, that's what you're asking, right?
Yes, sir.
So yeah, you have to take this point and write this distance as like sine theta and all. You take the components, find the height difference, and you can definitely do that. We will do all these kind of questions tomorrow for sure. We will do that. Okay. So that's it, guys. That's it for today. If you have any doubts, text me and we will talk about them tomorrow. All right. So thanks so much and bye bye. We will meet again in tomorrow's session.